Hello and welcome back to the Cisco CCNP route training through TrainSignal. My name is Joe Reinhardt and I am your instructor. And one of the things that occurred to me as we approached the whole subject of the route exam was making sure that we have a pretty solid foundation upon which to build. And that being the case, I thought it wise to be able to just do a general review of IP routing, some of the fundamentals and mechanics. I think that'll serve well as we continue to move ahead. This particular lesson will begin by taking an examination of routing theory. What's involved, what are the building blocks, what are the fundamental principles. Then we'll look at classful versus classless routing, static and default routing, and then finally some fundamentals, just general fundamentals of dynamic routing protocols. Now first, let's review routing theory. We want to take a little bit of a look at what is Layer 3 IP routing as far as the definition is concerned. Then we want to break apart the components of routing, what's involved, what are the piece parts, the fundamentals. Then we want to look at network and host routing because they are different. And then finally some overall principles to remember as we move into a larger examination of routing protocols. Now first, let's look at a definition of IP routing. Again, this is a Layer 3 process, and essentially it's moving information across networks. It involves, of course, both source and destination addresses. You can look at the diagram to the left. It takes place at Layer 3 of the OSI model, the network layer, rather than at Layer 2. At Layer 2, what takes place is bridging, which is operationally different than routing. Usually there's some kind of an intermediate node involved. For instance, you can see in the diagram to the left, host 1 sending traffic to host 2. It passes through a switch on a specific VLAN. It then goes to one router interface. It's then transmitted across some sort of transit network. It could be the internet. It could be a corporate network. Then it arrives at a router on the other side, a different VLAN, and then it ends up on host 2. So there's usually several devices involved with IP routing. Now there are specific logic processes that dictate how routing takes place. These are sometimes referred to as algorithms, and all routing protocols, as we'll look at later, use a routing algorithm. And really the goal of routing in general is to select and use the most optimal path available. Now keep in mind something else is that routing is bidirectional. All the information that is being sent from host 1 to host 2 then has to travel back from host 2 to host 1. For instance, if you ping a particular address, there are two legs to that particular journey. There's the journey to the destination and the journey coming back. And sometimes what happens with network engineers is you can forget that it's a two-way process. It may be transmitting just fine, but the reception coming back may be inactive. And one final note in looking at this whole basic definition of IP routing is sometimes IP routing is referred to as IP forwarding. And there are a couple of places within the grand scheme of routing and switching where sometimes multiple terms can be used. So when necessary, we'll actually supply alternate terms that you may see or read in the literature. Now, what are the different components of routing? Again, it has to do with optimal path determination. What is the best way to get from, in this case, host 1 to host 2 across multiple possible routes? The IP routing table actually contains the information in order to be able to at least begin the first step of that journey. And in the IP routing table, there are several critical pieces of information. Usually there's a prefix or a network and mask combination. There's an outgoing interface. There's a next hop address. And then there's a metric, and a metric is just simply a measurement of the reliability or preference of a particular route. Now, there are several sources for populating the IP routing table, and this is fairly universal. It starts with directly connected routes or interfaces. Interfaces that are configured on a router are considered to be the most believable because they have to actually be functioning. Then there are static routes which are manually configured by a network administrator. And then finally there are dynamic routes which are learned by some sort of routing protocol. And these are generally the three ways the IP routing table is populated. Now switching is different than routing. It's sometimes one of those things that can sort of be lost in the nuances of understanding the way the process works. But routing is the process of figuring out which way to send a particular packet, but switching is actually the process of taking the information from one interface or device and changing it to the other. Layer 3 routing means that the IP address, the layer 3 address, is consistent throughout the entire journey. It never changes. But the layer 2 address is changed or switched at each device. For instance, going from host 1 to VLAN 1, very straightforward. But once it's then being sent to router 1, the MAC address is changed because the source and destination addresses from a layer 2 perspective change at each hop. It changes many, many times, and this is why it's sometimes called switched or swapped out. In addition, there's also the principle of switching from one interface to another. And again, this is a number of different devices, number of different times this happens, and there may be other TCP/IP protocols that may factor into the whole mix along the way. For instance, ARP, or Address Resolution Protocol, which maps the layer 2 and layer 3 addresses. So routing and switching is part of the process of moving a packet across the destination network. Now I wanted to take a moment to distinguish between host-based routing and network-based routing. Network-based routing, for example, is mostly what we're talking about. But host-based routing is a very simple type of logic that's used by individual devices. They do have a simple routing table of sorts. For instance, if you go into a Microsoft Windows-based machine and you go to the command line and type route print, you'll actually see the rudiments of a very simple routing table. In fact, we'll do that in just a moment. Now, the routing logic takes basically two forms. Is the device on my network or is it not on my network? If it's on my network segment, I just send it directly. It's typically unicast transmission. The device is local, it's sent just fine. If not, then it's sent to a default gateway. Essentially, that just becomes where anything is sent if the device does not know the actual address. So you can see it's a very simple logic pictured to the left. But understanding host-based routing can be important to solving obscure networking issues. I actually was called upon to assist at a state agency in Washington State, and they were having trouble with some remote devices being able to reach some servers. And these involved actually some non-Cisco devices, so I immediately thought right away that might be part of the issue. But after examining everything that was going on in their network, what the problem was is there were two interfaces on these particular servers, and the server was getting confused because it didn't know which one of those interfaces to send the traffic across. So I ended up having to configure a host route to be able to point out to a specific interface, and voila, everything worked. So host routing is not an insignificant part of the routing process. It can actually come in quite handy. To illustrate the point of host-based routing, I want to do an actual demo from my particular notebook that I use for instruction. What we want to do to be able to show this principle is first you go to the command prompt, which you can either use CMD or command. Then voila, here we go. And one of the things that's possible in this is to be able to look up the routing table. And it's a simple device, syntax, route, print. Now look, there's a lot of information here, far beyond what we're going to look at directly. Notice there's a whole IP version 6 routing table, which we'll be handling later. But you're showing your interfaces. But here's really what we want to look at, the IP version 4 route table. You can see the loopback addresses that are listed. But in this particular case, you can actually see listed out the particular network that this device is on, some metrics, and so forth. So this is kind of a piece of the host-based routing principle. Notice here it's actually looking at specific subnets here to be able to determine whether or not to be able to send something on its network. And then there are also devices and gateways. In this case, this is the default route. So if it doesn't know where else to send it, it's going to send it out this particular gateway that's pictured here. It's a very simplistic way of being able to look at routing from a host perspective, but this kind of gives you an idea as we look at the larger picture of IP routing, some of what's involved. Now, in contrast with host-based routing, and really the focus of what we're going to be talking about in these entire set of lessons as well as this particular one, is what's known as network routing or network-based routing. It's much more extensive in scope. It's not from the perspective of an individual device. It actually can be quite vast. It involves a number of intermediate devices, routers or layer 3 switches, And this is usually the type of routing that's referred to as far as Cisco devices are concerned. There can be all sorts of logic, protocol, network level mechanics, and it's really the core focus for network engineers in this particular exam, the CCNP Route 642902 exam. So host routing, network routing. Now, some overarching principles that you always need to keep in mind with routing are things such as longest match. In IP routing, the most specific route is always going to be preferred, and the reason why is because the more number of bits, the larger number of bits that are being dealt with, the more specific a route is, the more preferred it's going to be. And this can be referred to as longest prefix, for instance, using CIDR notation. We have 192.168.11/32. This is sometimes referred to as a host route. It is about the most specific route possible. It's going to automatically be preferred in a routing table over 192.168.10/24 because it is much more specific. It is a longer prefix or a longer match. Another way of referring to it is a specific route will be preferred over a broader summary route. Using another example, 192.168.10 using standard notation is going to be preferred over a 192.168.00 essentially /16 route or 255.255.00. The general is always going to be trumped by the more specific. So remember longest match because that's one of the things that can throw you a little bit if you don't keep that in mind. Another is a valid connected route. The interface that the address exists on must be operational and functioning. If you created, for instance, 24 loopback addresses on a Cisco router, and they were all in administratively shut down mode, none of them would show up in the routing table. If you have a particular interface that's not functioning and has an IP address on it, it's not going to show up either. It has to be a valid connected route, something that is on a functioning interface. Now, on a functioning interface, you can have a number of secondary addresses, but as long as the interface is up and functioning, you'll be able to actually see that in the routing table. So those are some principles to keep in mind. Another principle, and the final one we'll wrap up on at least this section, is unicast, broadcast, and multicast. And the reason I bring this up is because routing protocols will use a number of different mechanisms for sending updates and hello messages. There are unicast messages, and these are true also with just ways of centering information in an IP network. Unicast is you're sending from one device to another. It's a lot like sending a letter to a friend. You have a source address that's very specific, a destination address that's very specific, and it's only intended to go from one point of origin to one destination. Very simple and straightforward. Unicast. It's specific. Broadcast, on the other hand, is what typically happens with television, going to a very large number of viewers. It's not aimed at anyone in particular, anyone specific, but it's very broad and general. On IP networks, the 255.255.255.255 address is the broadcast address. It's designed for every device that's in that particular network segment. And then there's multicast, which is a little bit more like a club where you have to have a membership to get in. Multicast is sent to a specific group, and this is usually within the 224 to 239 or Class D address ranges. So keep in mind that with routing protocol operations, you're going to have unicasts, broadcasts, and multicasts in terms of functionality. Another important aspect to understand in IP routing are the terms classful and classless. We want to take a little bit of a look at this because it actually impinges on how routing protocols operate. We want to take a quick review of the IP address classes, what classful routing involves, how classless routing works, and then this is really the point of this, when classless protocols act in a classful manner because it can impact what your routing tables look like. To begin with, let's do a quick review of the different IP address classes. And this is IP version 4. We can talk about IP version 6 later in a separate lesson. But originally, the Internet Protocol standard specified 5 different address types, A, B, C, D, and E. Class E was considered and labeled as experimental. It was really never used, and it's far beyond the scope of anything you and I are probably going to have to discuss. You can see the table to the left lists leading bits, octet range, network bits, and host bits, and those sorts of things. But Class E is largely irrelevant. Class D specifies address space for multicast operations. And just a moment ago we talked about unicast, broadcast, and multicast. It's as a subject, multicast is beyond the scope of what we'll be discussing in IP routing, but it does have functionality that's important that we'll talk about later. Classes A, B, and C, however, are very commonly referred to and identified very broad groupings of IP addresses that had similar characteristics. In this particular case, certain number of bits in the host portion of the address and a certain number of bits in the network portion of the address. Now, the whole A, B, and C class was deprecated in favor of CIDR, or classless interdomain routing. It had a lot to do with being able to conserve addresses, because there were small organizations, small in terms of addresses, that received these very large Class A blocks, and essentially large amounts of them would end up being wasted or not used. And so one of the ways to be able to control the explosion of the IP routing tables was to be able to change from this class hierarchy to something a lot more scalable. Sometimes this Class A, B, and C is also referred to as major network numbers or major network boundaries. And this becomes important later when we talk about things like auto-summarization. But Class A, B, and C, pretty straightforward and likely something you already ran into on the CCNA. Classful IP routing could actually be referred to as class-based IP routing, which just basically meant an IP address was pretty much inseparably bound to the class to which it belonged. A Class A address would always be a Class A address, couldn't be a Class B address, and couldn't be treated as anything other than a Class A address. What I mean by that is the network and host portions of the address were considered fixed. So 8 bits in the network portion for Class A, 16 in a Class B, and 24 in a Class C, and then the converse, 24 bits in the host for Class A, 16 for a Class B, and 8 for a Class C. It assumed as part of this that if you were doing subnetting, you were using the same network mask for everything. So you might use a /24, but you have to use it for every part of the network as you're carving up the address space. You can't use a /24 in one spot and a /30 in another and a /25 in another spot. And part of this is because the classful routing protocols did not transmit subnet mask information in routing updates, so it just had to assume everything was the same. And this led to something called static length subnet masking or fixed length subnet masking. SLSM is what it's sometimes referred to. And because of that, discontiguous addressing was a problem. If you had a 10 dot address network on one side, a 10 dot network address on the other, and in between you had a 172.16 address in the middle, you would have problems with that because essentially the network is being split up by this foreign network in the middle. And so that's sometimes referred to as discontiguous addressing, and it wasn't supported in the whole classless world. So because of that, and because of the explosion of the routing tables on the internet, something had to be changed, and classful routing became classless routing. Classless routing pretty much threw away the whole Class A, B, and C mentality and changed it to sometimes what's referred to as CIDR, or classless interdomain routing. It was prefix-based routing. In other words, you would take a prefix, you would take whatever the prefix is, say how many bits were part of the subnet mask, and then you would transmit that. And because of that, you could subnet, meaning carve up an address space. You could supernet, which means being able to summarize a larger address space. For instance, if you had so many Class C addresses, you could actually aggregate those together in a prefix that really doesn't belong on a Class C address because you're aggregating. Because all the network information devices care about now is what's the prefix or network and what's the mask. Because of that, routing updates included the subnet mask, so then devices would know what kind of addressing it was really dealing with, how big the prefix was, how long it was, what was involved with it. And this is sometimes referred to as VLSM, or variable length subnet masking. Now you could use a variety of masks in the network and it really didn't matter. You might use a /30 for a simple point-to-point link. You might use a /24 for a LAN. You might use a /28 for a WAN connection. But the point is, at the end of the day, the routing protocols knew what that meant. Because of that, there was support for discontiguous addressing. And, for instance, an internet service provider could send out 1 or 2 announcements with this large number of addresses aggregated down to a simple statement or two, instead of having to send this very large number of routing updates with things that are more specific. So classless routing. Since most modern routing protocols use classless addressing, and classful addressing is this ancient relic of the past, why should any network engineer care about classful routing at all? I'm glad you asked that question. There are specific occasions when classless routing protocols act in a classful manner. For instance, if you wanted to, just for grins, you could go into a Cisco router and put in no IP classless, and it would immediately make all the routing protocols act in a classful manner, back to the A, B, and C hierarchy. But that's largely a lab exercise. More specifically, and to the point, some protocols use something called automatic summarization, and summarizes networks to the nearest classful boundary. In essence, acting in a classful manner, even though it's a classless protocol. The bad news is it's frequently enabled by default, this auto-summarization. EIGRP, RIP, and BGP will just do the classful summarization by default. It's disabled by issuing the no auto summary command in the routing protocol configuration mode. But knowing that in advance, when you're putting a network together or you're looking on the exam or whatever the case might be, knowing that if you don't disable auto summarization, your classless routing protocol is going to act in a classful manner. So keep that in mind when you deal with these various protocols and the quote-unquote features that come with them. No discussion of IP routing would be complete without touching on the subject of static routes and default routes. And specifically under this particular part of the lesson, we're going to look at connected routes, static routes, and default routes. Connected routes represent the very first source of information for populating the IP routing table. But there are several caveats. It just doesn't happen auto-magically, as I like to say. There are 2 conditions. The first is the interface has to be fully operational. It has to be in an up-up state. When you actually log into the Cisco command line and you issue the show interface, for instance, fast Ethernet 0/0 command, an entire plethora of information is returned. The first line says fast Ethernet 0/0 is up, line protocol is up. The first up has to do with the physical interface itself. Is it physically working? Fast Ethernet 0/0 is up, meaning it is fully operational. The next part says line protocol is up. It means that the layer 2, in this case Ethernet, keep-alives are functioning and operational. This means that both layers 1 and 2 are operational on the interface. If both of those are not true, then the interface will not populate connected routes from that interface to the IP routing table. The second condition is there has to be, understandably, an IP address configured on that interface. It either has to be there configured with the IP address network subnet mask command or by DHCP. The IP address DHCP command would be at the command line for the interface. There's an older command called IP address negotiated, but it means the same thing. Either way, there has to be an IP address on that functioning interface in order for it to be represented in the IP routing table. Now, output from connected interfaces or routes is similar to what you see here pictured on the left. This is actually from router 1 in our lab environment. You can see here that there are a number of connected routes: 192.168.12.0, 172.16.134.0, 172.16.12.0, 192.168.11.0, 10.1.1.1, and 192.168.1.0 are configured. These are connected routes. That's what the C means. You'll notice when you look at the second part of the screen, just down about 4 lines, you'll see all of the codes explained. And C, the very first one, is connected, and it means directly connected routes. And as a result, they're considered inherently reliable because the device knows about them directly. So connected routes, very much a part of the IP routing table for the local router. The second that we already discussed is static routes. These require input from an engineer or network administrator, and they are manually configured in the device, whether it's a router or a layer 3 switch. Either way, they are treated the same. It's the simple global configuration mode of command of IP route, whatever the prefix is, the mask, the next hop, and the metric. For instance, we could put in IP route 192.168.2.0 space 255.255.2550, and then if the next hop address was 172.16.12.2, that by itself would be enough. You can actually also just point it to an outgoing interface, but if there's a problem with the interface, that could become rather interesting. And then a metric if you want one. And sometimes a metric can be helpful. For instance, if you want to make sure that that route's preferred over all others, you could put in a metric of 2, or you could make it higher if you wanted it to be a floating static route of sorts. For instance, you could put in several routes pointing to different destination networks and put in higher numbers in order to only make those usable if one of the main ones goes down. It's sometimes referred to as a floating static route, often used with backup routes. So static routes, manually configured by a network administrator. Default routes can either be learned dynamically or they can be programmed in statically. And what a default route does is it essentially says if you can't figure out where else to send this based on the IP routing table, if it's not there, send it this way. And again, it requires input, and the syntax is very specific. IP route 0.0.0.0, and the mask is 0.0.0.0.0. That is the equivalent of any. Remember principle of longest match. This is the most general route you could possibly configure. So if all the specific routes have been exhausted, this is sort of the catch-all at the end. And you'll notice here, in looking at the left, this is from router 4 in our lab. It's actually listing a default route with an administrative distance of 2, for example. We'll talk about administrative distance later. Whenever you see an asterisk, that is actually a default route. So here it's listed as a static route. That's what S means, recall. And then it lists the prefix, the mask, and the next hop. It is sometimes referred to as the gateway of last resort. In fact, if you look sort of in the middle of the page, it says gateway of last resort, and it actually lists that. So default routes can be very useful for pointing to the internet. They can also be very helpful if you have essentially a stub network where there's only one point of entry and one point of exit. You don't necessarily have to spend a lot of time configuring a lot of routing protocols or static routes. You just put in a default route and you're good to go. But you always need to be careful to make sure you can anticipate how that's going to impact network operations. So now that we've considered classful and classless routing, connected routes, static routes, default routes, now we want to actually dive into the general fundamentals of dynamic routing protocols. And we need to start first to understand what is the purpose of routing protocols. What are they designed to do? 2, the classifications of routing protocols. 3, algorithms and routing metrics. And then finally finishing up with administrative distance. So what's the purpose of routing protocols? Routing protocols are designed to automate the process of sharing routing information among devices. It goes without saying that manual configuration static routes can be very time-consuming. If you have a handful of devices, 2, 3, 4, 10, maybe even 20, it may not be that time-consuming to put in static routes. But when you deal with networks with hundreds of devices, having to manually change something every single time, one by one, can be very cumbersome. Another thing is secondary routes can be configured, but they may not take changing conditions of the network into account. So that's another aspect. Another term that you should already know from your CCNA days is the process of convergence. Convergence is the time it takes for all the routing tables throughout the network to be synchronized. And it's the process of building all available networks and making them available, obviously from the perspective of a specific device. One of the things about routing protocols is it can help prevent the introduction of human error into the network routing process. I cannot tell you the number of times that I have transposed a number or put something in incorrectly and had it make things difficult for me. For instance, when I was trying to log into the firewall that is guarding our lab environment, I kept having difficulty. It was a new device. I had to program it, went through all the process on that, and wondered why in the world it wasn't working for me. Well, it's because I had gotten a number wrong. So I wasn't able to ping it, I wasn't able to log into it, and that simple kind of thing can be introduced into networks inadvertently when everything's dependent on a manual process by people. So one of the final things that routing protocols are designed to do is to compile a collection of routes, choose the best route based on a specific set of criteria, and that criteria is called a metric, and the metric is different for each routing protocol. So this is the overarching purpose of what routing protocols are designed to do. They're designed to make the life of the network administrator easier and have the network operate in a more seamless fashion. So there are several different classifications of routing protocols. First, there are IGPs, or Interior Gateway Protocol. And as you can see pictured to the left, this is basically the idea of how an IGP would operate. There are several different networks. There are paths to several different networks. And if there are changes, then it wants to be able to let the other devices in the network know there's a change. But Interior Gateway Protocols specifically are designed within the use of a single autonomous system. And an autonomous system is generally defined as a network under control of a single group or organization. Administrative control is sometimes a moniker that's put in there as well. Some of the IGPs have very limited scale, such as RIP. RIP is limited to 15 hops. And yet in production environments, I've still managed to find RIP operating. So there's a number of different current IGPs. There's RIP, Routing Information Protocol, version 1 and version 2. There's OSPF, Open Shortest Path First. There's Enhanced Interior Gateway Routing Protocol, EIGRP. I'm not listing IGRP because it's been deprecated. And then there's Intermediate System to Intermediate System, ISIS, with which I have a particularly rocky history since it was a difficulty point on a number of my CCI lab exams. But these are some commonly used IGPs. Then, in addition to IGPs, you have EGPs, Exterior Gateway Protocols. And these are designed for use between autonomous systems, not within an autonomous system, but between. So you have Autonomous System 1 and Autonomous System 2. They may have their own IGPs. One may be running EIGRP, the others running OSPF. It doesn't matter. And then an EGP is what's used to go between them. Frequently, it's used between customers and service provider environments for multi-homed internet connectivity. Often, if you have multiple internet connections to different providers, you have to use an EGP. And it's also true with MPLS type services. I worked for AT&T for 5.5 years, and we had a number of MPLS based services, and they all involved the use of an EGP. The currently used EGPs include, and actually there's only one EGP. There used to be an EGP called EGP, but it's been deprecated for a number of years, and it's actually BGP, or Border Gateway Protocol version 4, which has stood the test of time and is the definitive EGP. Algorithms and routing metrics. Different protocols use different algorithms and routing metrics to be able to determine what constitutes the most optimal route. They're all designed to measure different things. For instance, the first protocols ever in use for IGPs were distance vector. And the algorithm for metric calculation in distance vector is the Bellman-Ford algorithm, named after the people that came up with it. And essentially, it measures the shortest logical distance to a particular network. It may or may not be able to select the most optimal route. Frequently, a distance vector protocol will not be able to suggest or choose the most optimal route, simply because it may, for instance, like RIP version 1 and 2, just simply rely on hop count. How many devices away is something? But if one interface is a 100 meg circuit and one is a 64K circuit, it's not going to be able to distinguish between the two because all it cares is how far is it to that, not even taking into account what's the bandwidth on the interfaces from a particular path to a particular destination. Frequently, there's a slower convergence process because it essentially relies on what's called routing by rumor. In other words, whatever it gets from a neighbor, it considers to be gospel, and it just says, great, that's a shorter route, I'll put it in. Well, what if it's wrong? What if something's malfunctioning? What if it's configured incorrectly? Well, then that's a problem. So the distance vector routing protocols include RIP version 1. Simple hop count was the metric. Up to 15 hops, 16 was considered unreachable, which, by the way, just has to do with the fact that it's a 4-bit metric, and that's as high as it could count. And then there was IGRP, which was designed to replace RIP. It's dealt with a very complex metric. Distance vector routing algorithms. Along came link state algorithms. It was developed, or I should say the algorithms was developed in 1956. It's called the Dijkstra algorithm, or the Dijkstra shortest path first algorithm. And it depends on every router in the network building a database of all the links that it knows about, then also receiving information about other links from other routers, and the cost to reach those particular links. And this is referred to as the LSDB, or link state database. It's not a routing table. It's essentially a database full of vectors for how to reach a particular set of networks. Based on that database, each one of those devices having an identical copy of that, using itself as a reference point, then calculates the best path to a particular destination. Much more routing intensive, a lot more CPU intensive, but much more accurate. Formal neighbor relationships and some things we'll talk about later in upcoming lessons. But link state routing protocols essentially are two. There's open shortest path first, OSPF, and then intermediate system to intermediate system, ISIS. Now, one of the things about ISIS to understand is it is not, strictly speaking, an IP routing protocol. It was a CLNS, or OSI protocol, that was retrofitted to work with IP, and so there's some things about it that are very unique and different. So keep that in mind if you ever have to deal with it. So link state algorithms. Finally, you have hybrid routing algorithms. It has elements of distance vector routing, and it has elements of link state routing. So it's not strictly speaking either. It's kind of a combination of the two. The algorithm that's used for metric calculation is called the diffusing update algorithm, or DUAL. And the idea of DUAL is to have distributed route processing rather than centralized route processing. It does depend on formal neighbor relationships, which makes it similar to OSPF in that regard. But it creates a composite metric that accounts for bandwidth and cumulative delay in choosing the best route to a destination prefix. Now, as such, it has some traditional distance vector loop prevention mechanisms, hold timers, split horizon, and so on. So that's the distance vector portion of it, but it has these formal neighbor relationships. The hybrid routing protocol includes enhanced interior gateway routing protocol. They didn't have an IGRP version 2, they just built a whole new one with a more complex metric and a variety of things. So sometimes it's referred to as hybrid or balanced hybrid or advanced distance vector, but they all mean the same thing. Finally, there's path vector algorithms. Path vectors actually try to use the path vector or best path selection algorithm, which sounds like what we've already talked about, but it operates on an entirely different mechanism. For instance, BGP is what's involved in here. It doesn't rely on cost or distance, hop count, but utilizes multiple factors to determine which paths through the network are loop-free. Because it's decentralized by nature, it possesses the ability to scale and support extremely large networks such as the Internet. It operates in an entirely different way. It may seem like a distance vector routing protocol, but it actually goes about it in an entirely different manner. It does not have an intimate knowledge of everything throughout the network like OSPF does, but it knows enough to be able to understand, okay, which one of these paths will work and is loop-free. Obviously, BGP4 is the definitive routing protocol and path vector, and a topic we'll be discussing at length later. The final subject in our review of IP routing is the subject of administrative distance, which is actually a critically important point to be able to understand and to be able to work with. Frequently, using a single routing protocol in larger networks, and larger networks are the focus of the CCNP, it's desirable. Very few people want to run multiple routing protocols, but sometimes it's not always achievable, and there's a variety of factors, a couple of which are listed here. You could have legacy environments, a particular set of devices that only supports an older protocol like RIP or something like that. There could be mergers and acquisitions. You may be just fine running your EIGRP only routing domain, and you're informed that an OSPF routing based organization has become a part of what you're doing, and you can't just rip it all out overnight. There has to be a phase-in process and a period of time where they may have to coexist. There may be political factors. A individual company I know a number of years ago was still running AppleTalk. I know, hard to believe, but it had to do with the fact that the CEO of the company had a very fond attachment to it. Now, granted, that's not a routing protocol, that's a routable protocol, but the point's the same. Political factors can influence network architecture decisions. So one protocol may not be something that you can do for a variety of reasons. And because of that, you need to be able to have a way or a mechanism to establish preferences for routing protocols when multiple ones are running, not just in a network, but on a particular device. This is where the concept of administrative distance comes in. Administrative distance is local to each Cisco device, and it is specific to Cisco routers. And it assigns a level of believability to the source of a route using a hierarchy. It's pictured here to the left. These are the ones that essentially are the defaults. Connected routes are 0 because they are inherently believable. Static routes are more believable because they're manually configured, even if they're done with transpose numbers. EIGRP summary routes are 5. eBGP is 20, and you might notice that iBGP is 200 for reasons we'll talk about later. But of all the IGPs, you'll notice that EIGRP internal routes are going to be preferred. IGRP, oddly enough, is still on the table, but you have OSPF, ISIS, RIP, and so forth and so on. But the point is, this is the preference. If you program multiple routes with multiple routing protocols, let's say you put in EIGRP, OSPF, and RIP, EIGRP is going to win because it has an administrative distance of 90. The lower the number, the more preferred it is. But the thing you have to keep in mind is that distance, not only is it local to each Cisco device, but it is configurable. These are the defaults, but you can change them. For instance, I did a set of CCNA labs where part of the solution in one of the labs for a backup route was to have all the EIGRP routes holding in reserve with a higher administrative distance, and then if for some reason that all went down, the OSPF stuff would immediately take over. It was actually a very interesting lab. But the point is, you can actually change these values when necessary using the distance command under each one of the routing protocols. So router EIGRP 100, for example, you'd put distance, and then you can actually change the administrative distance. So a couple terms to review. Host-based routing. Remember, this is the simple routing performed by a device host, whether to send data locally on its own network or to a default gateway if it doesn't know where that network resides. Longest match. This is the principle of IP routing, which states that the longer or more specific routes are going to be preferred over the more general ones. Always remember that. Classful routing was IP routing based on the original class A, B, and C addressing classes. Classful routing was IP routing based prefix and mask lengths, ignoring class altogether. IGPs, interior gateway protocols, dynamic IP routing protocols used within an autonomous system. EGP, dynamic IP routing protocol used between autonomous systems. And then finally, administrative distance. This is the numerical value specifying the preference or believability of the source of a particular IP route. So what have we looked at? We've gone over routing theory. We've reviewed classful versus classless routing, static and default routing, and finally the fundamentals of dynamic routing protocols. Thank you for your attention as we've been reviewing these very important and foundational principles, and look forward to talking to you again.